A similar force to the force of friction, which occurs when two solid objects are in contact, is drag forces. Drag forces are the forces opposing motion of an object traveling through a fluid. Now, fluid, you immediately think liquid, but in reality, a fluid is a liquid or a gas. It's anything that flows. So, drag forces occur when objects move through air. For example, a car driving on the highway experiences a drag force because of the air hitting the car. A skydiver falling from a plane experiences a drag force. Or a liquid, right? When a boat goes through the water, it experiences a drag force. When a fish swims or an otter swims through the water, they experience a drag force. The equation for the drag force is given here, and we'll go through what each term means. The force of drag opposes motion. Remember, force is a vector. This is just giving the magnitude of that force. The direction depends on which direction the object is moving. For a skydiver falling down, the drag force is up, right? It opposes the motion through the fluid. So the drag force is equal to 1/2 times c. This c is a drag coefficient. It depends upon, again, the surfaces in contact. Because the Olympic Games are coming up this summer, for those of you watching this recording later on, when the Olympic Games come up again, you might hear about swimming, you might hear about shark suits. The idea that swimmers can clothe themselves in a large suit that reduces the drag they experience as they swim through water. That's this drag coefficient. If you make c small, you make f small, the force of drag. So otter skin, for instance, the oils in the skin on the hair on otters is very low drag coefficient, allowing them to effortlessly swim through the water, or you and I, not so much. This is the density of the fluid. Right, so this rho, it looks like a P, is a Greek letter, is the density of the fluid you're flowing through, right? Higher density fluid gives you a bigger drag force. When you walk in air, you barely notice the drag force. When you try to walk in a pool of water, up to your neck in a pool of water, try to walk forward, you definitely feel that force. So the density is important. A here is the cross-sectional area of the object moving through the fluid. I don't know if any of you have done this as kids. I remember doing this. Driving in a car, you stick your hand out the window. And if your hand is flat, if the air is coming in this direction, your hand is flat, you feel a bigger push backwards. But if you turn your hand to the side, and the air is still coming this direction, it cuts through the air more easily. Now, the air density doesn't change. The drag coefficient of your skin on the air doesn't change. But this cross-sectional area does. It's why we design cars the way we do, right? Low profiles, especially sports cars, to give the smallest cross-sectional area to allow objects to flow through. Think of a submarine, right? A big tube. We sail a submarine the tube this direction. We don't change the submarine on the side. Submarine moves like this. The submarine does not move like that. It doesn't present or towards the camera. Submarine doesn't move like that. The submarine moves like this to cut through the water more easily, presenting a smaller cross-sectional area. Now, if you're a skydiver, you can actually take advantage of this, especially competitive skydiving, where they make all of the neat configurations as they fall through the air. If you need to speed up, put your arms to your sides, put your legs in, you have a smaller cross-sectional area and you fall faster. Pull your arms way out, right? Pull your arms way out, just put your legs way out, cross-sectional area increases, and the drag force increases, slowing you down. And of course, that's how parachutes work, right? A parachute is when a skydiver says, oh crap, I really need to slow down. opens the parachute, a huge cross-sectional area pops up above their head, slowing them down considerably. And then finally, V here, V is the speed of the object through the fluid. How fast is the object moving through the fluid squared? Notice that there's a square here. So the force depends on the speed. You can kind of see how that makes sense, right? If you're in a car and the car is parked and it's not a windy day, there's no drag force on your car. As your car gets faster and faster on the highway, the speed increases, the square of the speed increases dramatically, and so the drag force increases. And this is what causes gas mileage loss when you're driving on the highway. The friction in the wheels and the engine is a small amount of energy loss, but if you're driving 75 miles an hour or 70 miles an hour, whatever it is on the highway, set the cruise control on, you're driving straight, most of the energy of the engine is used to fight the drag forces experienced by the car. So your car is actually more fuel efficient at lower miles per hour. If you drive at 55 miles an hour to your destination, you will save fuel compared to driving at 65 miles an hour or 75 miles an hour. And this is also why cars have an upper limit. I don't recommend doing this, but if you take your car out and you floor it and you have the engine go as fast as you can, eventually your car will peak. It will reach a top speed and won't be able to go any faster. Even on a flat road, it won't be able to continue to accelerate because all of the car's engine, all the energy it's producing, is going to fight the extreme drag force at that high speed. So this is the equation for drag force. It depends on, again, the coefficient, which is something that you have to experimentally measure. It's not something that can be immediately determined. The density of the fluid, which is actually easy to measure, or you'll be given that in a problem. Cross-sectional area, and speed of the object. So for a skydiver wearing a suit, the drag coefficient won't change. The suit doesn't change as you fall, so the object stays the same. Density of the air changes a little bit as you fall. If you've ever watched the Felix Baumgartner Red Bull jump, where he jumped from basically a weather balloon at 65,000 feet, the density of air definitely changed for that skydiver. But for average skydiver jumping at 10,000 feet, the density of air doesn't change dramatically. It changes a bit. Cross-sectional area, again, the skydiver can put his or her hands in or out and change their profile. But what really changes for skydivers is speed. Right? When a skydiver initially jumps out of the airplane, their vertical speed is 0. They're, of course, traveling at some very high horizontal speed, but their vertical speed is 0. There's very little drag force, at least vertically, on their body, and they fall very quickly. But as they continue to fall and get faster and faster and faster as gravity pulls them down, the drag force gets larger and larger and larger until eventually the drag force actually balances the force of gravity. When those two forces balance, when the force of gravity downward, the weight of the skydiver, is balanced by the drag force upward, and the reason the drag force is upward is because it's opposing the downward motion of the skydiver. When those two forces balance, there's no acceleration. If there's no acceleration, there's no change in velocity. No change in velocity, there's no change in speed. The skydiver reaches what's called terminal velocity. So terminal velocity is the speed at which the drag force on an object is equal to the force of gravity on that object. And this is typically used in skydiving. But also could be for any object that's dropped. A penny falling from the Empire State Building. Will a penny that falls from the Empire State Building kill a person? The answer is no. No. A penny, no matter how high you drop it, will not kill a person. It might sting when it hits the top of their head, but it will not go through their skull. Because pennies and skydivers and any object that's dropped will reach a maximum speed called the terminal velocity. Should be called the terminal speed, but that's not the terminology. So we have the skydiver here shown, happily falling. Now the drag force, remember, changes depending on the speed of the skydiver. Initially, when the skydiver first jumps, there's just the weight of the skydiver downward, and there's no drag force upward, so the skydiver accelerates down. If these forces balanced right away, the skydiver would just float after jumping out of an airplane because there would be no net force on the object, therefore no acceleration on the skydiver, and the skydiver wouldn't fall. But as the skydiver continues to fall, as the acceleration is downward, the velocity and thus the speed increases with time. Eventually, the speed gets to a point where the drag force balances the weight. At this point, the skydiver cannot fall any faster. Now, I say that, you can cheat a little bit and pull your arms in and increase your terminal velocity, but then you get to a point where you can't fall any faster. So, theoretically, what does this mean? Well, let's look at Newton's second law and a free body diagram on this object, the skydiver. Well, Newton's second law states the net forces on an object are equal to the mass of that object times that object's acceleration. Well, what forces are acting on this object? Well, we're just going to worry about the y forces, and that's only two forces really acting on this object right now. So there's I define up to be positive, there's the drag force upward, so it's positive, and then there's the weight downward, which is negative direction, and that's equal to mass times acceleration. But at terminal velocity, the acceleration is 0. The object is no longer accelerating, it's no longer gaining speed. So if A is 0, that means this whole equation is equal to 0, which means that F sub d minus W, the drag force minus the weight, has to be 0. The only way it's 0 is if these two forces are equal to one another. So let's set them equal to one another. Here's the drag force, 1/2 c rho a times v squared, is equal to the weight of the object, which is m times g, mass times acceleration due to gravity. Well, I can algebraically solve this equation for the speed. That's what I want to know. What is the terminal velocity of a skydiver, or any object that falls? Well, when we solve this algebraically for v, we get this equation here. The speed, v, is equal to the square root of 2 times the mass of the object times the object's acceleration due to gravity, divided by this drag coefficient times the density of the fluid times the cross-sectional area of the object. And let's look at this equation in a little more detail. Let's try to make sense of this intuitively. What does terminal speed depend on? Well, it depends on the mass. Objects with a higher mass actually have a higher terminal velocity. That kind of makes sense, right? You drop a hammer and you drop a feather has a lot less mass and reaches its terminal velocity very quickly, a very small terminal velocity as it gently floats downward, whereas a hammer reaches a much higher terminal velocity and accelerates down more quickly. In air resistance. If there's no air resistance, there's no drag forces, a feather and a hammer will fall at exactly the same rate. It's only because of the air resistance on Earth, in Earth's atmosphere, that a feather and a hammer fall at different speeds because of this drag force. It depends on g, the acceleration due to gravity. And again, that kind of makes sense. The harder Earth pulls on you, if I could magically turn up g and make it a stronger gravitational acceleration, the harder Earth pulls on you, the faster you should go downward. If g is 0, if there is no gravity, there's no gravitational acceleration, then there is no terminal speed. You don't fall, right? If gravity is 0, you just float. It's inversely proportional to this drag coefficient. The bigger the drag coefficient, the lower the terminal speed. And again, that kind of makes sense. A low drag coefficient means that you're more smooth or slippery through the fluid you're traveling in. So a small c leads to a big V, a big speed. The density of the fluid depends on the terminal speed. Again, that makes sense. Falling through molasses, imagine a very dense metal ball falling through honey versus falling through air. And then, of course, the cross-sectional area. Right? The terminal speed of an object depends on the cross-sectional area, and skydivers can take advantage of that by, again, expanding their arms, increasing their area, decreases their terminal speed, allowing them to slow down. If someone jumped later than they did, they can slow down and catch up to them, or let their friend catch up. Or you can put your arms together, reduce your terminal speed, reduce your surface area, which increases your terminal velocity, making you fall faster. But just note that algebraically, all of you should be comfortable enough with your algebra skills to manipulate this equation to go from this step, solve for v, to get to this step. And then once you're at this step, this is the terminal speed, you should be able to manipulate this equation to solve for any of these variables. The previous drag equation largely works with fast-moving, larger objects moving through air. If the object is very small, therefore has a very small radius and also small mass then, is going very slowly, so it has a very slow speed, or is it a denser medium than air, then the drag force is proportional to the speed, not the speed squared. This relationship is called Stokes Law, and it's given by the following relationship. F sub s, being Stokes' formula here, force, according to the Stokes Law, is equal to 6 pi, it's just a constant, times r, where r is the radius of the object. We can assume the object is roughly spherical in this sense, so if it's not, you can approximate. Times nu here, which is the viscosity of the object, of the fluid. Instead of the object density now, like with air, we're now worried about the object's viscosity. How thick, if you will, is the fluid. Now viscosity, you might have heard like automotive commercials where their oil has the lowest viscosity. Viscosity is just basically how easy is it to flow through the fluid. Oil with a low viscosity is what you want for your engine. You don't want thick oil in your engine. It would prevent your engine from running. So think of viscosity. Honey has a very high viscosity. Oil has a very low viscosity. And then finally, v here is the speed of the object in the fluid. Note that it's not squared in this equation. It's a linear dependence. So this is for, again, denser mediums than air. For the viscosity of the fluid, again, can be determined by, if you know what you have, you can use lookup tables, or your book might give you the viscosity of honey, the viscosity of oil, the viscosity of water, and so on. Radius of the object is the object, the radius as it moves through, and the speed of the object, assuming that the object is going slowly. This is the relationship. This force, this drag force here, opposes the motion for small objects in dense mediums traveling slowly.